Oh, good afternoon, Dr. Biswas and other engineering students. Today we'll be analyzing a damper system with torsion being applied to it. So here we have our system. As you can see, we have two parallel dampers connected to a gear, which is having a torque applied to it in the positive theta direction. And as this gear turns, it will be lifting this mass of M1 in the positive direction. And here you can see it's confined by a dampener and two springs that are in series. Okay. And here we're going to make some assumptions. We're going to have a fixed floor and wall. We're going to have an ideal spring and dampener systems all around here. We're going to have a frictionless ideal system right here at this point of contact where this movement's going to happen. We're going to have a lumped mass point for both the gear and the mass, the block down here. No slip on rack and pinion, and as well as initially at equilibrium. So here we can have our free body diagrams, and as you can see, we summed up the two dampeners right here with B equivalent in the opposite direction of the torque that's being applied. And we also have that gear train translated as the force of M1. Now, that is not to be confused with gravity. This is simply the force of this block and that connection that they have. And we have the free body diagram of the block over here. And you see we have that same force, F of F1, on the gear track in the opposite direction. And we also have our dampener here on the left, and then the springs in series equivalent, the force of that right there as a whole, represented as one. So here we have, this is how we calculate our dampeners that are in parallel. It's simply the summation of the two. So 2.1 Newton meters seconds per radian, we get 4.2. And then for springs in series, it's the reciprocal, the addition of the reciprocals. And so this would be 1/Ke equivalent, but we went ahead and transferred it over to this side. That way we can just get our answer right off the bat. And after doing so, you get 17.778 Newton meters for the equivalent spring of the springs in series. Our input is going to be our torque that's being applied on the system, and our output is going to be the displacement of X. Now, here are the other givens that we were given in the problem: the mass of the block, the diameter of the gear, as well as the two series case springs. B1 is the dampener, and then B2 and 3 are the parallel dampers up here, as well as the mass of the gear. Now, from the mass of the gear, we needed to find the moment of inertia. So in order to do that, you do 1/2 the mass times the radius squared. Radius, of course, being d/2. So here we have the equation that we use right here, and our units are going to be kilogram meters second, meters squared. So applying the forces to the free body diagram, here we have the torsional gear, moment of inertia times the radial acceleration equals some of the torsion. So we have the applied torque minus the force of M1. Now this is in the X direction. This isn't a radial force. So we're going to address that in the next equation down here. And of course, minus the B, the equivalent dampener force times radial velocity. So in order to turn this force, this linear force into a radial force, we have to use this conversion right over here. Theta equals X/R. So since this is in the X direction, we need theta R here. Now, we're going to take out the theta because Fm1 is not a function of radial displacement. So it's not a function of theta, it's just Fm1R. It's the force times the radius. and that'll give you your linear velocity off the gear. So here we have the simplified equation. Inertia plus equals the torque applied, and we also do the same thing for the block free body diagram. We have the Fm1 in the x direction minus the force of the dampers minus the force of the springs, and that breaks down to this mx double dot plus the b1 x dot plus k equivalent x equals the force of the mass one. So here we have our two equations again, and again our relation right here. We know that after we notice that we can put them into each other. Fm1r, we can set these equal to each other. So when we do that, we get this equation, Ix double dot over R. Again, okay, this theta dot is going to turn into X, because of this relation over here, they're going to turn into X dot over R and X double dot over R respectively. So we have Ix double dot over R plus B equivalent X dot over R plus the radius of Fm1 on the gear side times what Fm1 equal to on the block side. Of course, equal to close parentheses after the multiplication of R equals the torque applied. Now, we're going to take the Laplace transform in order to get the transfer, or to put this in a in the transfer function. As we end up getting xs is equal to I over R plus rm1 s squared plus B equivalent over R plus rb1 s plus rk equivalent is equal to T of s. And then we can throw that over 1 to get our transfer function symbolically, and we basically have 1 over this equation that we just said. So here is the that same equation. We're simply just plugging in values. Right here, I had a little discrepancy with the units, but then I figured out that when you divide it by this R instead of an equivalent R, this division of radius already accounts for this to put it in the into the x domain instead of the theta domain. So we simplify these fractions over here. We get x over s over T of s is equal to 1 over 11s squared plus 18.325 s plus 4.445. And that's going to be our transfer function. I simplified it down more by taking out the 11 to put it into a 1 as the coefficient of the highest power down here. So that would be easier to put in the state space function. So here I have it written out in variables again. And here I start putting it in the state space. X1 equals X, X2 equals X dot. And then I took the derivative of those. X dot 1 is equal to X dot, which is equal to X2. And then here you have X dot 2 is equal to X double dot, which will be equal to this this function, which will be equal to the torque applied minus this minus the E equivalent minus the K equivalent all over the M equivalent right here. So here I'm building our matrices. The x dot vector is equal to ax plus bu, and y is equal to cx plus du. Here I have our x dot vector. A 0, 1. X dot 1 is equal to x2, and then x2 dot is equal to RK equivalent, or negative RK equivalent over our MK equivalent, minus our B equivalent over our M equivalent, X1, X2, X1, X2, and then plus our 1 over M equivalent on our U over here for our input. And then C is just equal to, y is equal to x of 1. So y is equal to 1 of x1 for displacement. And and 0 for D. There's no input there's no second input. And then here we have our vectors written out in this form right here. Here we have our four matrices, A, B, C, and D. And here I am finding the inverse Laplace to put this back into the time domain so that we can find the x displacement. And yes, here it is. So I took the 1 out of 11 out. 1 over s squared is equal to t. And then I took a 1 over 18 out, and we get s minus 0.256 after we divide this as well by 18.325. And the Laplace transfer of that is equal to e to the negative 0.256, because this is similar to the 1 over s minus a. And then you get e to the at. Sorry, a would be negative 0.256. And then here is the MATLAB functions that I built, or to plot it. This is equal to 1 over 11. 1 over 11s is equal in the numerator, and our denominator is going to be s squared plus 1.66s plus 0.404. And here we did the transfer function and then applied right hand side. And here you can see our transfer function right here. That's what this represents. Thank you for your time. Hope you have a good day.